Another type of addition reaction to carbonyls is the addition of cyanide and bisulfite, which behave very similar to one another. So we've seen that aldehydes and ketones react with water. They will also react with other nucleophiles, namely cyanide. And when they react with cyanide, they produce what are called cyanohydrins. The typical reaction is where you take an aldehyde or a ketone, right, where R could be an alkyl group or a hydrogen. You treat it with sodium cyanide in water, followed by adding sulfuric acid. So this is a two-step process. First step is with sodium cyanide in water. Second step is with sulfuric acid. One of the reasons for this is, you could react it with HCN, and the reaction itself, number one, is very slow. Number two, is very dangerous to work with HCN. So we typically don't do that. Again, two steps: sodium cyanide in water, followed by adding a little bit of sulfuric acid. The result is you add HCN across the double bond. So cyanide adds to the carbon, and then the oxygen is protonated. And this is what is called a cyanohydrin. The mechanism of this looks like this. Again, the carbonyl carbon is the electrophile. Cyanide is a nucleophile. It attacks that carbon, displacing a carbon-oxygen double bond. And you end up with the negative charge on the oxygen. So you've created a carbon-carbon bond through the nitrile, and you have an alkoxide. And this is the first step, right? And then the second step is by adding acid, sulfuric acid typically, to that aqueous solution. You then form the hydronium ion, which can then protonate the alkoxide. And you end up with the cyanohydrin. So here are a couple of examples. Here I have 2-pentanone reacting with sodium cyanide and water, followed by that sulfuric acid, and I get, so notice what's happening here. The carbonyl carbon is converted into a carbon with an OH and a CN attached to it, right? So it goes from an sp2 hybridized carbon to an sp3 carbon, OH, so I'm getting an alcohol and a cyanide. And when a cyanide and alcohol are on the same carbon, that's where I call it a cyanohydrin. Like the addition of water, cyanohydrins are fairly unstable in basic conditions. In acidic conditions, they're a little bit more stable, but in basic conditions, it's an easy way to reverse the reaction. And as a matter of fact, this is something that is found in nature. You find cyanohydrins in nature a lot of times as defense mechanisms of insects of some sort, where they can release cyanohydrins in their skin, and then those cyanohydrins get hydrolyzed rapidly, and they produce hydrogen cyanide gas, which in turn essentially can kill a predator that way. Taking a look at the mechanism of that, in basic conditions we have hydroxide. If we're talking about an aqueous solution, the hydroxide can react with the cyanohydrin and essentially deprotonate the OH group, and you form now the alkoxide, which we saw, and now this alkoxide can then reform the carbonyl and kick off the cyanide. So now you have the carbonyl reformed, cyanide is produced as well. Bisulfite, which generally is in the form of sodium bisulfite or potassium bisulfite, so sodium bisulfite, NaHSO3, adds in a very similar manner to that of cyanide. So here I have the Lewis structure of the bisulfite, sodium bisulfite, and the bisulfite anion has a pair of electrons on the sulfur. And so it will react with the carbonyl through the sulfur. So you're creating a carbon-sulfur bond. It does this with the help of that negatively charged oxygen. So what happens is the oxygen donates a pair of electrons to the sulfur, increasing the electron density on that sulfur, which makes it more nucleophilic. It can then use its pair of electrons to attack the carbonyl. We then break that carbon-oxygen bond, right, and the electrons go to the oxygen. So the result is this particular Lewis structure where I have an oxygen that has a negative charge. The next step involves deprotonation, protonation. So what we're going to do is we're going to deprotonate the OH group of that sulfonic acid, because we've essentially produced a sulfonic acid. And the OH is very acidic, so in water it can easily be removed, and you produce a sulfonate salt. And of course, now the alkoxide is going to be protonated by the hydronium ion that we just formed. And so we can protonate the alkoxide, and the result is this, right? So the carbon now has an OH group, an alcohol coming off of it, and a sulfonate group coming off of it as well. So here I take cyclohexanone, I treat it with sodium bisulfite in water, and I get my sulfonate alcohol.